Yeah, I will basically talk about some of the methods which are out there, how to evaluate them, and also about some new development. Yeah, the problem of explaining and the black box problem has been there from the beginning. Even the old work of Frank Rosenblatt, he said that the perceptron can be considered a black box where something goes in and something comes out. And nowadays, of course, our perceptrons grew in size. So we do not rely on one layer, but have like a much complicated structures with tens or hundreds of layers of nonlinearities, and therefore explainability has been an important topic in the last decade. And basically, there are different ways to explain. What I will here focus in the talk, at least in the first part, is explaining by attribution. So what we want to do is we want to have, for example, an image which gets classified by the neural network. In this case, the image is classified as a pool table. And then we have an explanation telling us which pixels, which areas in the image have contributed most to the decision. In this case, we see that the shape of the table, the legs of the pool table, but also the balls, the pool balls, and the cues are important, whereas stuff in the background is not so important. So in this case, we have a clue, and yeah, you can see that the network is really focused on the table and the balls. There are different ways of constructing these attribution maps. I will not go too much into detail here, because I think my colleague Grégoire also gave a talk on explanation methods on the first day. I just want to mention that there are like perturbation-based approaches where the idea is that you perturb the input and see how these perturbations affect the prediction or the output. And based on this sensitivity to this perturbation, you construct your explanations. There are methods which rely on simple proxies, such as a gradient, or simple quantities which you can compute from your model. There are approaches which rely on a surrogate. So the idea is here that you do not explain the original model, but you first train a local surrogate and explain the surrogate. And finally, there are structure-based or perturbation-based approaches which kind of use the structure of the model. And one of the methods, LRP, layer-wise relevance propagation, which we developed, is a representative of this category. In LRP, the general idea was to explain predictions by decomposition. So we wanted to find a way to assign relevance scores, in this case Ri, to every input element, in this case to every pixel, so that these relevance scores measure how much this individual pixel has contributed to the prediction, so that the sum of the relevance scores then equals the model's output. In this case, the model has predicted this image as a rooster, and we see that the heat map tells us that the most relevant pixels are the camp of the rooster, the head, and everything around the head of the animal. Features like the feathers, for example, or the legs of the rooster are not so important. And how do you get these heat maps? What we propose with LRP is to first classify the image in the forward pass. Some of the elements in some of the convolution filters, some of the neurons in between get activated. They encode some things which are in the image. For example, some of these neurons may be responsible for encoding the flowers. Some of them may be responsible for encoding the feathers. Some of them may be responsible for encoding other concepts like tires of a car or the nose of a dog. In this case, these neurons which are related to other classes will not get activated. And in the end, we have a prediction. So the output neuron, rooster, gets activated. And what we do with LRP is we kind of want to redistribute this output value backwards through the network. And we don't do this in one step, but we don't want to do it layer-wise. Therefore, LRP is a layer-wise decomposition or layer-wise propagation procedure. And yeah, there are many ways how to do this. So a simple way, which we at first propose, is to take into account the activation and the weight, so the XI and the Wij. So the intuition is that neuron I should get a larger share of relevance if it gets activated as a forward pass, because then it means that it encodes some features which are in the image, which are potentially important for the prediction, such as the flowers or the rooster's camp. But also the weights, the Wijs, are important because they kind of, the combination of these features are aggregated and make up the prediction in this case. So these two features should be important. And there are other rules which we came up with. There is also a theoretical interpretation of this process. So this redistribution procedure can be seen as a layer-wise Taylor decomposition. So the thing which you kind of redistribute the quantity can also be described in this deep Taylor decomposition framework. And you can do this for each neuron in the last lower layer, and then again to the layer below, and again until you arrive at the input layer. And in this case, you will get relevance scores for every input neuron, which then you can visualize as a heat map. And the important thing here, we will come back to it later, is that also the intermediate neurons, the intermediate elements get relevance values assigned. And also there is a relevance conservation. So all the relevance, all the evidence for the rooster which goes through the network stays the same. Nothing gets out, nothing comes in. And it's just like a redistribution process. And it's in the end, you will have a decomposition of the prediction outcome in terms of pixel-wise relevance values, which can, in this case, can be positive and negative. So we have applied this technique to all different types of problems, to images, to medical data, to NLP, to videos, to sensor data, all types of problems. And basically a strategy which we wanted to perform at the beginning was we wanted to debug and validate the predictions. And what we found, so you can see it in the left upper corner, this is an example of the Pascal VOC dataset, a visual object classification dataset, which has been used for an international challenge. And what we found here is really astonishing, because we explained the winning method, the model which won this challenge. And we can see that the model was classifying horses not by detecting the horse, but by looking at the copyright tag in the left lower corner. And this is what we didn't at all expect at the time, that through explainability, through these explanations, you can immediately see that something goes wrong, that the model is not doing what it is supposed to do. And we found this kind of, we call this clever Hans effect. If you don't know clever Hans, you should Google it. It's on Wikipedia. There's a nice article about the clever Hans, which was also a horse, a real horse. But in this case, the classifier behaves like a clever Hans. So it classifies the image but it kind of, in the end, it is cheating. It is not solving the problem. It is not detecting the horse, but it is cheating by looking at the copyright tag. And why is it cheating? Apparently, in the data set which we had here, a lot of horse images have a copyright tag. This data set was taken from the internet. People, the organizers, labeled, or many people labeled this individual images, but nobody looked at all of it and checked the quality, and therefore in this case this effect was overlooked, that the copyright tag was often there in horse images. We also find this kind of effects also in today's data set. When you look at ImageNet, there were a lot of these kind of bugs, a lot of these flaws, which then influence the model. So you can use explainability for debugging or for validating. In certain cases, you can validate that everything goes well, everything works as expected. You can use explainability for optimizing your model. So we use this for pruning, since, as I showed you, we know not only the explanation, the relevance values at the first level, but also at the intermediate levels. So you can also, if you know which neurons are relevant or which connections are relevant, you can get rid of the non-relevant ones and prune the network. You can, nowadays we are working towards methods where we can directly use explanations to improve the model. We can directly include explanations into model training, into the loss. And we also have a lot of work on using explanations in the sciences for scientific insight. So in this example, we use this on some epidemiological data where we trained a model to predict of the mortality, the risk of mortality of children between 6 weeks and 3 years of age in Guinea-Bissau, a country in West Africa. And what we wanted to find is, we wanted to find common factors which have subpopulations which have a high risk of dying. In this case, for example, if the children do not have a mother and are born in a dry season, they have a much higher risk of dying than children which do not share these factors. So you can use explanations for all kinds of tasks which go way beyond just these visualizations. But the question, of course, occurs when there are a lot of different methods, which one to choose. So what is a good method? So I just explained like one method to you, LRP, but which method should one choose? And there is a lot of work on this issue. There is a lot of work on how to evaluate explanation quality. And basically the problem is that, in general, there is no ground truth, right? In general, if you classify an image, it's unclear, like, and you have an explanation, it's unclear like what to compare it against. Should, for example, for the case of the horse, it's maybe not the fault of the explanation method that the model is looking at the copyright text. It's the fault of the model. So it's like a really process which is so the quality of the explanation not only depends on the explanation method, but also on the model. So and people have developed different indirect measures, procedures to evaluate explanation quality. Here are just like some random subset of them. Later on I will give you also more, like measures like fidelity or faithfulness. Basically assume that an explanation should reflect the quantity being explained and not something else, which sounds reasonable. If I give you an explanation, it should explain the prediction and not something else, right? It shouldn't be a random explanation. And there are different ways to check this, to validate whether your explanation really does what it is supposed to do. An explanation should be understandable. This is maybe something which is much harder to fulfill, to make sure, especially in images. Maybe humans are quite good at interpreting images. When it comes to other types of data, when it comes to time series data, for example, or to proteins, sequence data, it's much harder for the human also to understand the explanation. Sufficiency explanation should be sufficient. The explanation method should have low overhead and have the explanation should be computed in reasonable time. These are just like few desiderata. This list can be much longer. And one way to evaluate faithfulness, one way to evaluate fidelity is pixel flipping or region perturbation, a technique which we proposed some years ago. Basically, the idea is that you regard the feature, if an input feature is deemed relevant, then removing it should reduce the evidence at the output. So basically, in other words, if your explanation method tells you that this pixel is relevant, or this combination of pixels is relevant, then by flipping them or by perturbing them, by adding noise at this location, this should have an effect on the output of your network. Otherwise, these pixels are not relevant. So there should be a connection between like the relevant map, the explanation, and the output of your network. Here is like one way to evaluate things. So we have three methods: occlusion, LRP, and integrated gradient. And you see these curves. On the x-axis, you have the percentage of pixels perturbed. On the y-axis, you have the output score of the network. And you see that if you randomly perturb the pixels, this is the red line, the curves goes down quite slowly. If you perturb the pixels which are identified as relevant by methods such as occlusion or LRP, as the green and the blue line, it goes down much faster. If you perturb the pixels which have been identified by integrated gradient, it goes down even faster. So in this case, it seems that integrated gradient is a very good method because it has identified the pixels which, when perturbed, can change the prediction behavior. However, as you see the pixels, the images of the dog, it seems really strange because the pixels which have been identified by integrated gradient do not really change the image much. So it seems that integrated gradient is not really explaining the prediction in this case, but it has found like a vulnerability of the model, and this flipped image looks like an adversarial example rather than an image where important features like the eyes or the nose have been removed. This just shows you that even you have like a meaningful evaluation scheme, things can be more complicated because you have to really make sure that you are explaining what you want to explain and maybe not explain on by constructing adversarial examples. This is something which we just observed and which you can see here. How do you evaluate understandability? It's much harder. You can use subjective studies. You can use ask a human to rate explanations. You can ask a human to do as additional task with the explanations. Here in this work, we also had a very simple proxy quantity. In this case, you can try to estimate the entropy of the heat map or the sparsity of the heat map with the assumption that if the information in the heat map is sparser, it's usually better for understandability. Sufficiency is also like a tricky thing because even an explanation which is faithful and understandable may be insufficient. So especially when it comes to textual explanations, if you ask why did the classifier predict this image to be a lighthouse? And the explanation would be because the classifier found a lighthouse in the image. Of course, it's a correct explanation, but it doesn't bring you any new insights. It doesn't bring you any new information. So in this case, like, explanations should be actionable, should give you some additional, should contain all the information needed to solve the task. But this is sometimes difficult to evaluate and difficult to visualize, because sometimes maybe individual pixels are important, sometimes interactions of pixels can be important. So like trying to figure out and explain these slight details can be tricky. Explanation should be robust. So in other words, if two inputs are almost the same and the predictions is almost the same, then the explanation should also almost be the same. They should be continuous in mathematical terms. And these are just like some desiderata which we kind of describe in some older work. There is a very recent toolbox where we implement over 30 different criteria, different evaluation schemes to evaluate neural network explanations. So we try to re-implement all the metrics which people have proposed for evaluating explanations. So this is something which is available, which you can use. And basically, here you see like just like, the different categories. So faithfulness, robustness matrix, localization, tests, complexity analysis, axiomatic approaches, and also randomization tests. So we kind of implemented different metrics which have been proposed and categorized them in different categories. And here you see that it's 27 metrics. I think by now we have over 30. So this slide should be updated. But basically, you can evaluate different aspects of the explanation. So this is something which people often misunderstand. Often people have the idea that there is one true explanation, but I think when it comes to evaluation, you should really ask yourself, what do you want to evaluate? What aspect of the explanation is important? And does the metric which you use really evaluate this particular aspect of the explanation? In other words, they can be, different explanation techniques can be performed differently on these different aspects. So if you have like, saliency maps, integrated gradients, gradient shape, and fusion grad explanations, which are implemented in our toolbox, and we evaluate these different metrics belonging to these different schemes, categories, and it seems that there is no method which is best in all these aspects. So at least not among the 4 ones. So this shows you that there may be even trade-offs in the evaluation, and this problem is still still in the development, and I think there will be progress in research on how to evaluate explanations, what trade-offs are there in the near future. And even there has been papers kind of checking proposing sanity checks, randomization-based evaluation schemes, and saying that when randomizing top layers of the model, and this works, for many attribution maps, they couldn't see an effect in the explanation. So saying that the explanation stays constant even if you perturb or randomize some of the layers, and from that they concluded that kind of explanations are lying, or explanations are not really doing what they are supposed to do. But other work found some problems with this testing. So I'm not going into detail here, but just want to show you that, or make you aware that these kind of things are still under investigation, and there are still many slight problems with evaluating explanations. It's not the case that there is one best evaluation technique, and because even if you use randomization tests, it really matters how you do things. Because, for example, here in this paper, they said that this integrated gradient method has this problem, but the authors of the integrated gradient method showed in a note which they published later that depending how you do the computation, if you also include the sign of the attribution or not, you can get much different results. So it really, the details how you do this evaluation can matter. And if you include the sign, things are good. If you ignore the signs, things are bad. So it's really, the details matter here. Also, we recently wrote a paper on the shortcoming of top-down randomization-based sanity checks, showing that SSIM, the similarity measure, is problematic because we can show that it can be maximized by random noise. So meaning that a random explanation in this case would be best, which is in some sense counterintuitive to what you would expect from an explanation, and also finding showing that also the way these randomizations were performed from the top-down perspective is also problematic, because it may be insufficient to change the prediction behavior and affect the output of the neural network. But these are details. I think if you're interested, you should look at the paper. But just to show you that this evaluation problem is still largely under discussion, and and there is still a lot of things one should investigate. We recently also proposed a ground truth based evaluation scheme, basically with the idea that if we would have a ground truth, we could then evaluate explanations very precisely. But the question is, how do you get the ground truth? In natural images, you don't know the ground truth, but here we constructed images. So we use this clever data set. This is the VQA, visual question answering data set. So you have full control over the question, you have full control over the image. And in this case, we kind of constructed an image, synthesized an image, and asked the question. In this case, we ask, what is the material of the large ball? And in order to answer the question, you need to look at the ball, and so you can take this ball as a ground truth, and then compare your explanation with this ground truth mask, and see how much overlap there is, because this is what you need to do to answer this question. And you see here is a list of different methods which we compared with using this metric. And you can also ask more complex questions where you need to consider spatial relations between objects, or count objects. For example, what is the material? What material is the large object that is left to the big purple metal ball? So you need to first find the big purple metallic ball, and then look for the large object which is left to it. And so in this case, you need to look at two objects to answer this question, and you can see that the explanation method, in this case LRP, is considering both these objects. So you can also here measure how good you can compare to ground truth, and also we'll see a ranking of different methods according to this evaluation scheme. So there are further approaches. I will not go into detail here, to have a proxy task. So you can use explanations to create a proxy task, and then perform the proxy task and measure and do the evaluation on the proxy task. This is what we did in NLP here. And there is also pruning. You could assume that if your method is good, it identifies the relevant neurons, so and you can use pruning and evaluate the quality of the or performance of your network afterwards. So basically, this evaluation problem has different perspectives, has different facets. So it's really like you have to be aware what you want to evaluate, what aspect of an explanation you want to evaluate. And basically my utilitarian perspective is that explanations are good if they provide some additional, in the best case, measurable advantage. So if you can do something with the explanation which you couldn't do before, then explanations have an added value, and there are different ways to measure this added value. So this was this evaluation part. I would just, before I end, I would like to show you some of our more recent work where we try to extend these attribution maps to concept-based explanations. So we try to move from attributions to concepts. What does it mean? I mean, I always showed this example in my talks where here we trained an age classifier. The age classifier was, when applied to this image, was saying that this, or the classifier says this lady is between 25 and 32, which is correct. And the explanation tells you that the eyes are important, but also that it seems that laughing is an important feature for being classified as young age. And sometimes at some point, someone asked me, how do you know that it's really the laughing? Because in this case, this lady also has a very white teeth. So how do you know that it's the laughing and not the color of the teeth? And basically, we don't know when we just look at these attribution maps. These attribution maps tell us where something is relevant, at which location, but it doesn't tell us what it is. It doesn't tell us, is it the color of the teeth? Is it the shape of the mouth? Is it the laughing, or what is it? And very recently, we kind of proposed an approach where we kind of enter into this XAI 2.0 domain. We call this from where to what, where we create more human understandable explanations. In this case, explanations which can be related to concepts. Concepts such as color of the teeth, or laughing, or these kind of concepts. So you are not only explaining in terms of pixel values, but you are explaining in terms of human understandable concepts. So how can we create these explanations? I will just briefly tell you our contributions here. So first, this is a picture which LRP does. So you kind of backpropagate the explanation for the prediction dog. And as I said before, you don't only have relevances for the input, but also for all intermediate filter or intermediate neuron. So you have the relevance values for all the elements of your neural network. And basically, what we thought is first to construct conditional explanations. We thought, if we know that this particular filter, this particular channel is focusing on the concept I, then we can just filter the relevance flow by adding this Kronecker delta to the formula and have a focused explanation of the prediction dog conditioned on the concept I. And you can also do it for other concepts. So here we have like a few examples: the concept eye, concept fur, concept snout. And what you see, which you wouldn't see if you just have this combined explanation, you see that the concept fur is quite important for the prediction, but it's quite distributed over the whole image. Therefore, it doesn't, you don't see it if you look at the combined heat map. But if you disentangle these different factors, you see it much better. So this is the first contribution. We can compute explanations conditioned on a concept which is human understandable. And we can disentangle these factors. We don't consider like this combined explanation, but we can disentangle the explanation in terms of human understandable concepts. But of course, the question comes: how do you know the concepts? How do you know that the channel is encoding the concept? The concept snout or eye or fur. How do you have this mapping? Of course, a priori, we don't know. We don't know which filters or which neurons are encoding what concepts. But there has been a lot of work on this. There has been work under the names features visualization, activation maximization, where people tried to understand the role of a particular channel or a particular filter. And basically what and usually if you want to understand what this particular channel is encoding, you, for example, find examples in your data set which maximize the activation of this channel. So this is called the activation maximization or database activation maximization. And what we propose, this is our second contribution, is to, instead of focusing only on the activation, we maximize the relevance of this particular channel. So we were looking for samples in our training data which are mostly relevant for this particular channel. So when classifying the samples, this channel has a high relevance. So instead of using activation, we take relevance as a criteria. Relevance computed with LRP, with the method which we use here. And you see here that using the relevance, you consider the context of the task much better. So here we see that for the prediction dog, this particular channel mostly encodes the faces and the nose of the dog. But if you just use the activation as a criteria, you don't get this context. So you identify reference samples which maximally activate this channel, but which for you as a human is very hard to say what they have in common. And the third contribution, we kind of found a way to clearly visualize in these reference samples what the important information is. So we assume we have found our reference samples for this particular channel, and then we zoom in by using the receptive field. We scale this zoomed in images, put it to the neural network and find the relevant part and just cut this out and crop the part which are relevant for this particular channel. So what you see here is the relevant part of the reference sample, which is relevant for this particular channel. And I will bring it together and now you will see what it all means. So how it works is we kind of have this input. In this case, this is a particular bird. And we classify this image of a bird by our neural network. And now we explain this classification. Usually we would have a combined heat map where we would see that everything is relevant. But here what we did is we kind of found the 5 most relevant intermediate channels. We found the 5 most relevant convolutional channels and the last convolution layer for this prediction. And then try to understand what these particular channels are encoding. So you see this conditional heat map. This is where this channels map to input space. This is what I showed you before with the nose and the snout. And you see this reference samples, the mask reference samples, and you see that channel 10, the one in the middle, is encoding red color, red stripes. So the color red seems to be quite important for the classification of this particular bird. So it's not only the fact that there is a stripe, but also the color, the color red is quite important. It contributes almost 2% to the classification. But the most relevant feature is the feathers, the texture on the feathers. And you see that channel 210 is, and channel 130 and channel 19 are encoding these different textures. And they kind of contribute a lot to the prediction. You can give names to these different channels, to these different things they encode. Channel 187 is mostly encoding black eyes of animals. The black eyes of a dog, black eye of a cat, and also the black eye of a bird. So the fact that this bird has a black eye is also quite relevant for the classification decision. So basically, our concept relevance propagation method is a combination of local XAI, where we want to explain individual predictions as a heat map, which I showed you before in my talk, and global XAI, where we want to understand the representation of the model. And here we kind of bring this together. We not only explain the individual prediction in terms of heat maps, in terms of showing where information is relevant, but we also show what it is. We show through examples. Through examples, we show what does this particular channel encode and what is the meaning of this. So we have an augmented explanation. And you can even look at the composition of concepts. So for example, on the right, you have a bird which was classified, and you can ask yourself, what is the most relevant channel in the next lower layer? It's channel 102. What does this channel encode? It is encoding animals sitting on a branch. And then you can ask what other lower level channels are important for the channel 102. In this case, you have channel 51, which is encoding horizontal bars. You have channel 506, which is encoding like feathers of something, and so on. So you can see the whole path of flow through the network of concepts which build other concepts, which then builds a prediction. This is something which was not possible before. You can even find also here, you can use this approach to find problematic cases. In this case, we have an image of a safe. It has been classified as safe. And you see that in the middle of the image, there are some Chinese characters, which are deemed relevant by the model. So the model thinks that these Chinese characters are important for the classification safe. And what we ask ourselves is what channels in the model are encoding these Chinese characters. So we found these channels. These are the 6 ones which you see here. We found them with our approach. And then we were asking ourselves, for which other images in the data set these 6 channels are also relevant. So it's like a reverse image search. We wanted to find other images where these channels are also relevant. And you can see it here. You can see other images like whistle, mop, screw, mosquito net, can opener, where these particular channels are also relevant. And abracadabra, you see that these images also have a Chinese character in the middle. So the same problem occurs here, and you found it by concept-based reverse search. But what is even more interesting here is that also for other images like puma or spider web, these channels are relevant. But for these images, there are no Chinese characters. There is just but for the neural network, the hair of the puma or the very thin lines of a spider web look like a Chinese character, because in both cases, the Chinese character and the spider web consists of very thin white strokes. And from the neural network perspective, these look all the same. So basically just removing these problematic channels wouldn't solve the problem. And we are currently trying to fix this misbehavior by finding more adaptive strategies. Basically, in the final slide, we have also demonstrated that the human can do better decisions with this concept-based explanations. I will not go into detail here, but we can find problematic cases, clever Hans artifacts with these concept-based explanations. And yeah, I think, I mean, what is still, when it comes to evaluation, because my one of the focus of my talks is also evaluation of explanations. I think we also need to think more about how to evaluate concept-based explanations. Not only like these heat maps, but really like concept-based explanations, which we have found here. How can we evaluate them? And it's a lot of opportunity and room for research here. And I think in the future we will see that all these different perspectives will dimensions will merge together. We have a lot of methods which explains the individual data points. So the data set level XAI, we have in our work, we combined it with model-based approaches, with global approaches. And we will also see in the future more work which will involve the human. So we will have a mixing of these different perspectives. And I think we need feedback loops from the human to the model, from the model to the human, to really make things practical. And with that, I want to advertise my new book on XAI. It's open access, so you can download it from Springer. We also have a lot of toolboxes. Quantus, I mentioned, we have Zenit. Zenit also has a lot of these PyTorch implementations of explanation methods. Also, there are other ones in Julia, for example, on TensorFlow. We have references, our proceedings paper, a lot of other papers where you can get more information about our work. And all these papers are also available on our homepage, heatmapping.org. And with that, I'm happy to take questions. Thank you very much.